Welcome and thank you for coming to our webinar. Today we will show you how to design and check concrete details using our application IDEA StatiCa Detail. As you can see on your monitor in the docking panel, we are using GoToWebinar and you are all in a listen-only mode. Please feel free to input your questions into a chat window and we will answer them at the end of this webinar. My name is Martin Rolny, and I have two of my colleagues here today, Jana and Philip, our product engineers, who will show us live examples in IDEA StatiCa Detail. IDEA StatiCa Detail deals with all parts of structure, also known as discontinuity regions, such as depth ends, hangings, walls, frame joints, brackets, and diaphragms. And of course, with respect to both ultimate limit state and service. Today, we will be talking especially about beam details. As you can see, we can design and check discontinuity regions like opening, depth end, and area above support, hook, and many others. And now we will show you two examples. The first will be change of cross-section of reinforced beam, and the second, anchoring zone of pre-stressed beam. So let me ask Jana to show us the first one.
Hello everyone, thank you Martin for the introduction. Now I will take the control and I will show you my screen and we can start. Okay. So I hope you can hear me and you can see my screen, and I have a new project in IDEA StatiCa Detail. Now I create the project itself, and in the first step we are asked to input the general data like concrete, grade, and reinforcement type, plus the concrete cover layer. I chose to use the concrete C30/37 and the concrete cover 20 millimeters. And now I can also, of course, set the name and author, and I can choose among different templates. We usually use them to speed up the process, but in my example today, I will start the general input. So the template will be, there will be no template and the project will be empty. So you can see how to create your concrete detail from scratch without using any template. So in the first part, we will, of course, follow the tree on the left side, and we start with the geometry. I will add the first item, and it will be the 1D member. Now I choose the cross-section, and it will be a rectangular cross-section, 500 millimeters on height and 300 for the width, or for the depth of the cross-section. I confirm, and this is my first member. Let me just adjust the view a little bit. I will also define the length of the member and the trimmed end. For the first member, I will set the trimmed end at the beginning, so it means at the left side. And now I want to add another member with different cross-section. So I can either use the plus button or I can copy the item. Now I have the member M2, and I will change the cross-section. Again, from library, I choose the rectangular cross-section, and now it will have a greater height of the beam. I confirm, and I will change the length a little bit. And now I can add it or glue it to the first member, and I will use the master and insert points. So the master points of entity M1 is number 3, and I want to link it with number 4 of member M2. And of course, I have to switch the trimmed end at the end of the member M2. So you can see in such a way we can define several members, and the beam continues at both sides of M1 and M2 members. And therefore, I don't have to add any supports because the supports are somewhere farther from this cut or from this detail of the concrete beam. So I am done with the geometry and I can continue to define the load. I have only one load case here created, therefore I will add another one with the plus button, and the first one will stay permanent, while the second one I will switch it to variable. Now we will input some internal forces for the load case. I will change to LC1, the permanent load, and I will define the internal forces at the section where the cross section changes. So it's for the entity M1, it's in x coordinate of 1 meter, and at this point I will input the bending moment 25.5 kilonewton meters. I want also to add some distributed load, therefore I will change the load impulses tab and add a line load with the plus button. The line load will be 5 kilonewton per meter, and I want to have it on both members. Therefore, I will copy the first line and I will change the master member from M1 to M2. Now we have the distributed load along all the detail. I'm going back to internal forces and I change the load case to LC2. Again, I will define the internal forces at the end of the change of cross section. Now the bending moment is 36 kilonewton meters, and the distributed load of LC2 has magnitude of 8 kilonewtons per meter. Again, copy the item and change the member. And we are done. Now I change the tab back to load cases and combinations. I have 2 load cases and I want to create 3 combinations of load. I use the button plus combination and press it 3 times. The first combination C1 will be the ultimate limit state combination. The second C2 combination will be a serviceability limit state with the characteristic load combination, and the third one will be SLS but quasi-permanent. Now all the combinations are in fact the same because all have the same combination rule, but I change it now in the combination table for all 3 combinations at once. So for the C1, I will input the partial coefficients 1.35 and 1.5 for LC2. The C2 combination, which is the characteristic, will have the coefficients of 1, and the quasi-permanent will have 1 times LC1 plus 0.5 times LC2 and confirm. And now to speed up the process of calculation, I will uncheck the first 2 items, which are the load cases, because I don't want to have results only for individual load case. I want to see the results for the combination, and this will save some computational time. So if you want to make only some partial analysis, only to evaluate one load case or one combination, you can use this checkbox, and everything that is checked will be calculated. Great. Let's move to reinforcement. Again, you can use some design tools like topology optimization, which I just started. And this is an advanced tool for finding the most effective volume of the concrete detail. So there is an iterative process, and in the end we see some marked compressive parts with the red color and parts in tension with the blue color, and all the colored parts are now 20% of all the volume. So these 20% of volume are the most effective ones. I can switch, for example, to 40%, etc. So you can use this tool to have some hint where the tensile areas and compression areas are. I will start the input of reinforcement by the button in the top ribbon. I can either leave the result of topology optimization switched on, or I can switch it off, also in the top ribbon. And again, the new reinforcement will be added by plus button. So my first item will be a group of bars, and it will be a group of bars along the bottom face of the M1 member. So I want to have it, I want to have 2 layers of reinforcement, and these layers will be 50 millimeters from each other. Then I change the diameter of the rebars, and in each layer there will be.
Okay, I'm sorry because we have some technical trouble, because I expect that you also cannot hear and see Jana's screen. Probably before we fix this trouble, I will ask Philip and he will show us, or we will continue with the second example, and then I hope we will fix the trouble and we will come back to the first one.
Okay, so let me continue from here, and again, our apologies for this. It's kind of outside of our hands. In the meantime, it is my pleasure today to show you a very nice example of Anchorage zone of the prestressed member. Although I must say that our detail application as of now aims mostly for the reinforced details. Nevertheless, in the case when we have straight cables like in this example, we can use it for sure with the anchorage forces from the cables, because we don't need the radial effects of the cables itself. So what I need to do is to run a new project, and let me choose a proper concrete grade in the wizard. So in my case, C40 megapascals, and also I will start with some template for a 1D detail, and I will modify this first one for the end support area. And the template has loaded two things. The first one is the member, and the second one is point support. So I don't want to bother you with the change of cross-section, which can be defined in the library. I'll just mention that we deal with a 2D model, and the calculation uses this discretized cross-section like this. And I'm not aware if many of you have attended previous webinars, so I'll just try to sum few important things in this project. The first one, sorry, is that I need to elongate the model because we usually say that we need at least 1.5 times the height of cross section after the last source of discontinuity. So in this case, I will need to make it a little bit longer to have a proper or desired and suitable length of the model, and all the results can be developed. Then, of course, I have a point support, which can be restrained in several directions or rotation. And yeah, in this case, we have a bearing plate support, which has its own mesh and own material model itself. You can change the properties here. I will also let them to be a default one. And I will actually make a different shape here on the left edge, and I will do that by an opening function, which is available here in the model entities. Of course, it will be rectangular, and it will be 10 centimeters wide and 0.45 meters high. And also, I want it to be inclined, so I'll apply a small inclination of 10 degrees to that. So you see exactly what's happening in the scene. And of course, I want it to be on the left edge, as I mentioned. So I will use this point number 8 as a master point, like this. And now I will move it upwards by 40 centimeters, like this. And when I go to another operation, for instance, I will copy that and move it, maybe make it a little bit smaller without the inclination, and I will relate it to master point number 1, and maybe move it a little bit down. You can see that the previous opening has cut this nice detail here. Okay, the last thing which I need to do is to introduce some bearing plates because I cannot apply a point load or point force, as it is a kind of a fiction from the 1D models. So we need to calculate as much close to the reality as we can. And the bearing plate will help us to distribute the load evenly, as it will be in the reality. So in load transfer devices, let me go for bearing plate, which is now placed on the top. So let's change that. And the first one I will place on edge number 5 here. Of course, I will move it slightly from the edge like this, and adjust its geometrical properties. So I'll make it 30 centimeters wide and 3 centimeters thick, like this. So you can see in the scene that this will be bearing plate to transfer 1 Anchorage force. And after I click on copy and make it on edge number 2, maybe move it a little bit downward, and you can see that I have defined pretty easily and quickly the desired complicated shape of this Anchorage zone. Okay, the software does not warn me that I don't have any clash or something unusual. So let me proceed to the loads, as we will load the model. In this case, I won't bother you with the variable load case, so I will delete it to omit everything, and I'll use just one load case for permanent effects, and I will go for internal forces tab later, because at first I want to show you what we'll include. We will use minus 50 kilonewtons per meter for a line load to introduce the bending. You can see it here. And also, as it has been mentioned, 2-point loads from the Anchorage forces. The Anchorage forces will be of 600 kilonewtons in a global X direction. For a bearing plate number 1. And now I can either copy that or add a new. It will be also 600 on a bearing plate number 2. And also I will incline it like this. Of course, you will see here that the IDEA StatiCa automatically recalculates the 600 to X and Z direction. So it won't be 1200 kilonewtons in X direction. You can see it's divided to X and Z part. At this stage, I need to ensure the equilibrium on the support. So let me go for it like this, and make the same value from the left and right. And also I need to ensure the equilibrium for the moment, like this. And the shear force, which is caused by the vertical part of an Anchorage force, so minus 104.2, as is mentioned here. Once I do that, you can see that I satisfied the needs. And the last thing is that I want to introduce the reaction about the 500 kilonewtons here. So if I apply the value of, let's say, 400 kilonewtons, I have a reaction of 504.2 kilonewtons here. And you can see that we compress the member and also we bend it like this. Okay. As has been mentioned, we have one load case which won't be checked to speed up the calculation, and we have 3 combinations, 1 for ULS, 2 for SLS checks, and if we want to change the partial factors, it can be done here. So let me actually go for the reinforcement. And the reinforcement has been loaded with the template. We can just adjust it. And of course, we could use some design tools, as my colleague Anna showed, but we expect that most of you knows how to reinforce the Anchorage zone. So let me just play with the reinforcement itself. I can change the diameter if I want, but for the stirrups, maybe I can show them to you. How do they look like? Because you can see them there. This is the tool to very easily define the distances. This means that it goes the 50 millimeters from the edge for the first stirrup. Then I can define that it should go 10 times 50 millimeters and fill in the rest after 150 millimeters up to the end, or up to the trimmed end of the member. Okay, this is all I wanted to show from the reinforcement. Of course, I could introduce few layers around the edges to cover everything from the detailing point of view. But what I actually want to show you are the results and a small comparison at the end. So let me go for a check button, which will run the nonlinear analysis. And you can see that a user does not need to define the mesh, the material models, the stress-strain relationships, and many more things. This is what we do automatically for you. And we also cover, as you can see here, the long-term and short-term calculations for the SLS checks. So there are actually two models run on calculation performed in this calculation. Hopefully in a few seconds we will get the results, and I will tell you something about them. But I don't want to go into details because I hope my colleague Jana will show it when we go back for the first example. So I'll try to show you the checks or results relevant to pre-stressed concrete. Yeah, and maybe one more remark. I have tuned the example to not satisfy the check, so you see what's happening if it does not satisfy. Okay, so this is the first picture which you can see. It gives you a very good hint or knowledge how the concrete detail behaves. You can see with purple color which rebars are in compression, which are in tension. With the blue color here, it will be much nicer in the second example, I promise. And the red color is for compression in concrete. So you can see that there is a big let's say a big concentration of the compression above the support and also from the Anchorage force. If you want to see detailing like this, you can see that we have minus 23 megapascals right here as an extreme value, and you can see also the corresponding values here in the table. If you want to see it for the reinforcement, for instance, I want to see the stress along the rebars. I can see it here. And yeah, of course, I can do it not just for a ULS, but also for the SLS. As I mentioned, it doesn't satisfy the check for the concrete. You can see it's not satisfying for quasi-permanent state for 45% of compressive strength. And yeah, we should come up with some different solution. We can either make a small haunch here as it used to be, so make the web a little bit wider in the Anchorage zone. Either we can shift the point support here a little bit to not concentrate the stresses. Either if we can decrease the Anchorage force. So this shows you that something is wrong and you can react to it somehow. Also, we covered the check for a characteristic combination for the rebars, the tensile rebars, of course. There is also a tool for crack width limit, and the software automatically calculated, as I mentioned, two states: the short-term, long-term total values of the cracks. And all we need to do is to define the proper limit. In Eurocode, it is set that for pre-tangent members, it should be 0.2 millimeters. If it's different in your national annex, please find it out and fill the proper value, because this value divided by this value gives you the utilization here, and that's how we ensure the check. If you want to see it again, if it's red or green, you can switch from the results to the utilization. Okay, and what I wanted to show you is that I can easily make a copy. And when I make a copy, I will delete the point support from the bottom very easily. Just go here. Well, I will delete it. It informs me that there are few internal forces related, mostly the reaction and so on. So I will delete it, also with the loads. And there are all the relevant loads for a compression. And I can run the checks again, because I want to show you that this kind of detail satisfies the checks when it's just the check of Anchorage zone. But what is very how to say interesting is that if you include both of the sources of discontinuities into one model, you have seen that it does not satisfy the checks. So the IDEA StatiCa Detail, or with it, you can benefit and see what's exactly happening, how these sources interact, and so on. So let me give a few more seconds. Last calculation, and we will see the results. Yeah, like this, and you can see that everything is green, everything is okay. Also, if we want to compare, you can see that we make a, let's say, small study. There is not so big concentration of stresses, and the stress flows like this. And when we include it, the banding from the point support here, you can see that also the compression or the strut goes upwards. So we moved the stress flow lightly, and you can see that it's very important to include everything in the model. Okay, that's everything from me. Maybe I will check if my colleague is able to finish her example.
Yeah, hello. I hope so. So let me share the screen again. I'm really sorry for the interruption. We have some issues with the GoToWebinar platform, and I don't know, maybe it's just bad weather in our office or something like that. So I don't know where the sound stopped, so I will just repeat the second item.
If I may, I think
Yeah.
we stopped somewhere around GB1. I think they haven't seen GB2.
Okay. So the GB1 is the bottom face reinforcement of member M1. We have two layers there with the distance of 50 millimeters. The diameter is 14 millimeters, and there are 3 rebars in one layer. Also, there is an continuous end at the left side, and on the right side there is extended end of 400 millimeters, so it goes also to the member M2. Then we copied the the element, and we define the bottom face reinforcement of M2 member. There is only one layer. The diameter is again 14 millimeters, and with 3 rebars in the layer. For the anchorage of the beginning of the rebar, I chose to use the standard band, and in the end the rebar is continuous as well, and I switched off the extension. Great, so now we can continue to define the top face reinforcement. Maybe I can just copy the second item, and I want to have one layer of rebars of 12 millimeter diameter and only 2 bars in the layer. And the reinforcement will be continuous at both ends, and I will change the edge from bottom to top. Okay, and I have to I have to switch also the end so that it extends of the from the M1, from M2 till the end of the detail, so it goes also through M1. So we have the longitudinal reinforcement, and the last step is to add some stirrups. So I will choose another item. It's a group of stirrups. They will have diameter of 10 millimeters, and I will just change the definition. So the first stirrup will be in the distance of 30 millimeters from the edge. Then I want to have 5 stirrups with 200 millimeters distance. You can see it here. Now I will define like more dense stirrups with the distance of 50 millimeters here, where there is the change of cross section, and in the end the stirrups will have distance of 200 millimeters. So I will just write A200. It means the rest of the member will have this distance of stirrups. Okay, it's always good to check the real 3D representation of the reinforcement, so you can really check that you have one layer with 3 bars at the bottom and one layer with 2 bars at the top. You can just go through the reinforcement cage from all sides. So, and if we are satisfied, we will continue to check the structure with the bottom in the top ribbon. And now the nonlinear calculation started, and all 3 combinations will be evaluated, and we will see the results for them. So the first view is always a kind of summary of all results. We should directly see whether we fulfill the code check or not, or what item did not fulfill, if any. But in this example, we can see only green marks, which means that we fulfill the check according to Eurocode. We can see the highest utilization of the members of concrete and of reinforcement, Anchorage, and then some serviceability limit state checks. In the first view, we can see all the parts of concrete in compression, also the magnitude of the tension in reinforcement, or for example, this top rebar is violet, which means it's in compression as well. And with the dashed symbol, we can see that the anchorage of the reinforcement is somewhere above 95%. In the table, in the central table, we can see the overall summary of the check of the ULS, and by clicking on the second line, we change the results to SLS. But if you are more interested in the detail results, so go to second tab, which is the strength. Again, first line corresponds to concrete check, the second one to reinforcement. You can see now you can see in the plot the utilization. It means the ratio of the actual stress to the limit stress. But by choosing different buttons in the top ribbon, we can also display the second principal stress, or the strain in the first principal direction and the second principal direction. We can also display the direction of the principal stress. And for example, the KC factor, which is the factor controlling the compressive softening of the concrete. So you can see that almost all the structure still have 100% of its strength, and in some regions the strength was already reduced. If I choose the second line, it means reinforcement. I can display all the characteristics for each of the bar of reinforcement. Again, in the top ribbon, we can choose between like utilization of strain or of stress, or directly the value of stress and strain. The second tab, or sorry, the third tab is the Anchorage. We can see that the rebars at the bottom face of the M1 has like 98% of the utilization of the anchorage stress, which is quite fine. And we can also display like directly the bond stress or the total force in the reinforcement bar, or the stress at the beginning if there is some anchorage type. So the first two tabs correspond to ULS combinations. So, and now we are moving to SLS checks. The fourth tab is the stress limitation ultimate state, the serviceability state. And we can see that for concrete and also for reinforcement, the combination C2 was taken into account. And again, we can see the utilization of concrete and of reinforcement. The next step is the crack. Philip already showed it. So we can define the different value for which is the critical one or the limit one, and then the utilization is calculated with respect to this value. And the last one, last step is the deflection. In this case, the deflection is not visualized in a really nice way because there are these trimmed ends at both ends. So the software cannot define any boundary conditions at the end. So there is only theoretical boundary condition, which is the clamping at the end of one end. But if you have a structure with which is statically determinate, then the deflection is displayed correctly. And of course, you want to present your results. So we will skip to report part. The last line in the left tree, we have to wait a few seconds to generate the report, and we can see all the results in the report. The report can be adjusted according to your needs. So you can choose what chapters will be included by only checking and unchecking these items in the list. Or you can also, for example, display only some results and checks. So I switch from show complete results to show selected results. Then I will just choose whatever I want to present, and I refresh the report, and it was adjusted already. And of course, you can either print the report or export it to like Microsoft Office document or PDF document to print it later or to send it to somebody. Okay, so that's all from my example. Now I will ask Martin about some questions if there are any.
Yeah, thank you, Jana and Philip, for your demonstration. Let me check questions from our attendees. Yeah, so here's the first one. User is asking whether it's possible to export the drawings into the Cad file. Maybe we can show it on your example, Jana.
I will show it directly. If we go to bill of material, we can see the list of all used bars of reinforcement, of course, then this 3D representation, the table, and there is a button in the top ribbon, export to DXF. I can save it, and of course I can open it in AutoCAD, for example, so you can see that you have all the rebars there. You can work with it further.
Yeah, cool. Okay, thank you, Jana. Let me check. Yeah, here I have another question, which is related to the second example, which was about a prestressed beam. In this case, the user is asking about the type of load combination, which was used for the check of CRED width. So, Philip, can we check your example again?
Yes, sure. I hope you see everything again.
Yeah.
Yeah, that's what I mentioned from the beginning. We aim for the reinforced concrete details. That's why we have. Okay, maybe I'll start here. For the SLS, we have, let's say, quasi-permanent type of combination, which is together with characteristic used for the SLS assessment in reinforced concrete. I understand that there are the compression state and crack width state limits defined in a code for a frequent combination. But yeah, sorry to go back. This is just a string or the name of the combination. It actually does not have anything to do with it, as you as a user define the partial factors. You can set these partial factors for your combination to align with the frequent combination, and this is the only place in the software where it will appear together with the report. And as my colleague Jana showed, it can be exported to, let's say, Microsoft Word, where it can be retyped to frequent, or you can use the user chapters to include them into the report and type it as a note, so everybody could see that you did not omit anything. It's just the way how the software works. And of course, as I have mentioned, this tool up here is completely independent from the code and national annex. So if your national code or national annex uses any type of combination, is just a matter of what have you used for it here. You can see it's C2. So this value corresponds to the frequent value. Yeah. Okay, I hope that's all from here.
Yeah. Okay. Thank you for this deep explanation. Before we finish our webinar, I would like to ask you to fill you a short survey, which will appear at the end. We will also send you a recording of this webinar. And if you would like to test our IDEA StatiCa, you can easily download a trial version from our website. Please do not also forget to check our resource center with a lot of other tutorials and examples. You can also watch recorded webinars and register to next coming events. So that's all for today. Thank you for your attention, and I'm looking forward to see you in the next webinar with IDEA StatiCa. Goodbye.